Hi, this is Keenan Maxfield. I'm an instructor for SEI. I'm going to give a brief overview of grounding, and I want to show you how current flows in a fault condition on a grounded electrical system. And I'm going to specifically talk about why we use a neutral to ground bond, at least here in the USA. So here's a schematic diagram of a grounded system. Now this could be the same for a grounded AC system or a solidly grounded DC system. Now a little caveat here is we have traditionally called non-solidly grounded DC systems, we've called them grounded, where instead of using a solid wire, we use something like a fuse. And as of 2017 code, those are now called functionally grounded systems as opposed to solidly grounded systems. And here I'm going to specifically only be talking about solidly grounded systems. Here is a diagram with a little bit more. I added a load here. This could be any appliance. I've got here a metal enclosure that is grounded through our EGC, equipment grounding conductor. And we've got some semblance of a load here that's using power. And this could be literally anything. So you just remember any component that is conductive, such as a metal enclosure or conduit, if it can be touched during normal operation, it must be grounded through our equipment grounding conductor, which connects back to our grounding electrode conductor, and which then connects to the earth. Whether we're talking about grounded or ungrounded systems, they all still have grounding as far as the equipment grounding conductor. And the primary purpose for equipment grounding is to make sure that there is no voltage between our exposed equipment or conduit and ground and the earth. Because if there were voltage, it would just flow through these wires, the EGC and the GEC. And you can see how this works. If the ungrounded conductor were to have a fault, the wire gets cut or something, and it connects to this grounded enclosure, the current will flow through this wire and back along the EGC. And remember, current can never flow unless there's a way for it to get back to the source. But this can just go right along the EGC, up through this neutral to ground bond, and back to the source. Now, in any code compliant system, there will always be some form of OCPD, overcurrent protection device, in this ungrounded conductor. And when that current flows through the ground and back to the source, it will trip that overcurrent protection device and will thereby de-energize any of this wire beyond the OCPD. But even without that, even if it were just flowing through there, this enclosure would still be safe to touch because it's still connected to the earth. You could still touch it while you're standing barefoot on the ground, and you will not get shocked. Now, if this EGC were missing, this OCPD would not trip. It would remain active. So if that EGC is missing, suddenly if this enclosure is energized, you would see there would be voltage from there to ground. And now if you were to touch it, that current would go through your body and into the ground and over into the grounding electrode conductor, up into this neutral to ground bond and back to the source. And you would receive anything from a shock to potentially electrocution. It can be anything from just a minimal tingling to death, depending on a lot of environmental conditions and the voltage. But in any case, it's something that we want to avoid altogether. If we were to not use the grounding electrode conductor, then if we had a different kind of a fault where the ungrounded conductor were to come into contact with something that actually was connected to the earth, let's make this a different color because it's not actually touching any of these wires that we're crossing. But if that were to come in contact with something else that is in contact with the earth, then suddenly we would see that there would be a voltage potential between our enclosures, which should have been grounded, and ground. And so again, if you are here and you touch this enclosure, then the current is going to go from this wire through the ground, through the earth, and then through your body and back to this equipment grounding conductor and back to the source. And again, you have the same problem that we had when we left off the equipment grounding conductor. Now, if you were to get rid of the neutral to ground bond, then if there was a fault, if this were to connect to the ground like we have here, then now there would be no current flowing and our overcurrent protection device would not trip. However, our grounded conductor, or the conductor that should have been our grounded conductor, now becomes live. And if you were to accidentally touch it, and you're standing on a conductive surface, then now the current would flow through that ground and back and into the earth, and then through your body to where you're touching that grounded conductor and back to the source. And again, we have the same problem that we had with either of the other two grounding omissions. So that's why it's important to have all the parts. The grounding electrode is very important. Our grounding electrode conductor, our equipment grounding conductor, and our neutral to ground bond. Now, one concern that people have asked about this neutral to ground bond is why doesn't current, if current is flowing along the grounded conductor, then why doesn't any current flow back into the ground system if it's connected there? And the reason goes back to the fact that current cannot flow into anything if there's not a way for it to get from there back to the source. So because it has nowhere to go, it cannot go into this ground system here. It will just continue flowing right on past to the source. I hope this makes sense. I hope this has cleared up some things. I hope you understand this better. If not, let me know and I will try to help you further. I love trying to explain these things, and just let us know. Have a great day. Thank you.